Good evening, all. Good evening, all online users. Today, we are going to start our second agenda item of the Electrical, Electronic and Telecommunication Engineering Section Committee, session 2023-2024. We are having an honorable guest in our house, Dr. KMSY Konara. On behalf of the ISL and the Electrical, Electronic and Telecommunication Sectional Committee, I would honorably welcome you, sir, for this event. So without taking much time, I would like to give the control of the house to Dr. Konara, who will be discussing about prospect of challenges of electric vehicle fast charging, which will be a very controversial and very important topic in the current context. So let me introduce Dr. Konara to the house. Dr. Konara graduated from the University of Pune in 2013 and completed his MSc in Renewable Energy from the University of Agder, Norway in 2016. His master's thesis was awarded as the best master's thesis in renewable energy at the university in 2016. He earned his PhD in renewable energy from the same university in 2023, focusing on the enhancement of charging resource utilization of a fast charging station with renewable energy resources. Dr. Konara's research interest in widely on renewable energy systems, electric vehicle charging coordination, and smart grid technologies. He has published over 30 peer-reviewed publications in international index journals and conference proceedings. Dr. Konara plays a vital role in organizing committees, advisory committees, and program committees for various international conferences. He is an awardee of the Presidential Award for the Scientific Publication in 2020. So without taking much time, I would like to welcome Dr. KMSY Konara to the house, and the podium is over to you, sir.
Thank you very much, Mr. Dushanta, for very generous introduction on me. Okay, very good evening to you all. So today we are going to discuss on electric vehicle fast charging. Okay, so this is actually very important topic these days as far as sustainable transportation is concerned. Actually, why we should know why fast charging, not slow charging, because we all know it is a severe challenge as a electric vehicle buyers. Charging time is a serious problem for us. In order to mitigate this severe bottleneck in proliferation of electric vehicles, the fast charging is the emerging technology these days. So that's why actually today I would like to share some thoughts and some important aspects, especially related with electric vehicle fast charging. Okay, I think there is no need of waiting of more. Let's step to the presentation. These are the main topics on which I'm going to discuss today. I think I no need to waste time just going through each and every at this point. Just let me to jump to the background. So when we consider the sustainability, the transportation we cannot avoid. Okay, so we all know the expected population inhabitants maybe by 2050, according to United Nations reports, may reach 9.5 billion. If I'm wrong, please correct me. Okay, if my memory is correct, it reached 9.5 million. So in order to accommodate this 9.5 billion inhabitants, we expect nearly 2 billion vehicles on the road. Okay. So if we consider these 2 billion vehicles, it is not really sustainable if we are going for internal combustion engine vehicles. Okay. That's why we have to give some thoughts on sustainable mode of transportation. Okay. Here, many governments, they are looking over this issue, sustainable mode of transportation. Okay. Here you can see in the figure 1, stated policies. If we go with the stated policies, that means with this forecastings, by 2030, the electric vehicle population with stated policies may reach 150 million. But if you are so ambitious and if we have some expedite or some government supporting programs, we may reach nearly 250 million, to be exact, I think 245 million by 2030 on the world's road. Okay. That means the attention towards the e-transportation is growing, and we can see when the number of electric vehicles on the road is increasing, in the sense we are increasing the power demand also. So that's how these challenges are coming. Okay, there is no doubt we can consider electric vehicles as a sustainable mode of transportation, because we very much aware when we consider the emissions, the electric vehicle emissions do contain less contaminants. Okay, so then the from health perspectives, of course, electric vehicles do have positive merits. Okay, and we know that the fossil fuels are decaying. So in order to power up vehicles, the electricity would be a good alternative. So in all these aspects, there are many processes, there are many advantages, but in order to promote electric vehicles, we have to see what are the challenges and what are the problems. So that is the main discussion in today. So I told you with some government incentives, especially in Europe, okay, the European governments, they are giving a lot of incentives to promote electric vehicles among the buyers of vehicles. Okay, so with these, with this type of programs, if you are so ambitious towards these sustainable scenarios, the electric vehicle fleet on the world's road going to be maybe 300 million by 2030. So that's what we can understand. That's what we can see here. This is the statistic I have taken from the International Energy Agency. So this is how now we are getting some sense, the sort of a challenge that we are going to have in the future with these numbers. Okay. And in order to understand the challenges and the problems, I would like to go from the very beginning just to have some good understanding. Here, this is the overview of an electric vehicle. This is the future, of course. I have included one slide here because this is a hydrogen vehicle. This is not much available in the on the world's road, but this is the future. We have to understand that. Okay, but from the architecture perspectives, there's no very big difference between the electric vehicles and the hydrogen vehicles. We will come there. Actually, this is the internal combustion engine based vehicle. So we are not going to go much into this one because everyone very much aware about this one. But when we consider an electric vehicle, the main power source within the vehicle is the battery. Okay. And we know in a battery, we store DC energy. Okay. And then in order to convert this DC energy into the traction model or in the motor, we have to use power electronic converter. Okay, so that is the basic idea. Actually, there could be two motors. One is a synchronous motor, another one is a DC motor. In any case, definitely we'll have to have either AC to DC conversion stage or DC to DC conversion stage. And here, this is the hybrid version. You have the internal combustion engine and also with the battery. This is just of a hybrid version of these two. Okay. And then this is interesting thing. I forgot to actually tell you. It's charging. Okay. So for the challenge, actually the challenges are coming with the charging and also this battery. There are two places where we are getting challenges. As far as battery is concerned, we are getting challenges. And also when we are, the charging is concerned, then we are getting another set of challenges. Okay. So we will go into these challenges and these problems systematically. And I told you this is the future, the hydrogen vehicle. In the hydrogen vehicle, the basic architecture is you have stored hydrogen, maybe in gaseous form or solid form. Okay, and you are having a fuel cell, because with hydrogen and oxygen, we can generate energy, okay, through a fuel cell. So then once this DC energy is generated, it is nothing but just like a battery electric vehicle. Okay, but here we are having serious challenges when we are going to store hydrogen in gaseous form. Safety issues are there. Safety issues are there. In other words, pressurized gas or pressurized hydrogen within a vehicle, within a hydrogen vehicle, is not very safe mode of transportation. And in the other place, if you consider this metal hydrides or halides, I can't exactly remember the word, but however, if you use solid form of hydrogen, then we are getting challenges with respect to the weight. So that's the thing we have to understand. Okay, but however, here we are not going to understand rocket science. This is just a basic architecture of an electric vehicle, just to understand the charging, because we are not going to understand the operation of an electric vehicles. We are more towards the power grid, because that's the place where we are getting challenges as electrical engineers and the power engineers. Actually, in order to understand these real issues which are related with electric vehicle charging, we have to have understanding about the availability of types of electric vehicles in the market. Okay, here, use this one, right? Okay, so here these are some available models. Okay, these are some available models of electric vehicles. But actually, in this table, I want to highlight one very important aspect, that is, please pay your attention for this column. The battery capacity. You can say, if you consider this Tesla, the capacity is 100 kilowatt hour. Okay, and also you can say here, when you come to Toyota Prius, here the battery capacity is 8.8, but it is a plug-in hybrid. But if you consider the battery electric vehicles, you can see here it is 32.3 kilowatt hour. Okay, that means you have to understand this range. You have electric vehicles whose battery capacity is 32.3 kilowatt hours, and also battery capacity 100 kilowatt hours. Actually, why do we need electric vehicles with this type of huge capacity variation, so capacity diversity in the market? That is a very important point that we have to analyze. If you consider the range, so this is actually autonomy comes with range perspectives and also the charging perspectives. If you consider the range point of view or the range perspectives, you can see the with one charge here, you can see with one charge, you can go 610 kilometer with this capacity. Okay. But here, if you consider this Volkswagen model 32.3, you can drive maximally 258 kilometers. So this is a very important when we consider the range and anxiety point of view. And that means in order to avoid range and anxiety, we have to go for high capacity electric vehicles. Okay. When we are going towards the high capacity electric vehicles, it increases the cost of the electric vehicles. That's the problem. So then we have to understand at the moment, nowadays, in order to avoid the range and anxiety, the available solution is high capacity electric vehicles, but it is no longer sustainable. Why? Or most of the people are not affordable to buy the Tesla Model S. That's the thing. Okay. So that's why we have to very innovatively think how to overcome these challenges. Okay. Solutions are there. Now we are going towards that. Okay. Then that's why I told you the battery capacity is a very important parameter when we consider charging, slow charging or fast charging. And here there is another important thing I want to highlight. Actually, this used to be a problem, but now at this moment, it's no longer a problem. That is the battery technology. Here, you can see nowadays, the battery technology is lithium ion. Battery technology is lithium ion. Actually, why we use lithium ion? Mainly because of the high power density and high energy density. At the moment, the average energy density of lithium ion batteries is 137 kilowatt hour. Sorry. Okay. This is the average energy density. Because energy density and the power density of a battery technology is very important to decide whether we are going for slow charging or fast charging. Okay. Why? Because the thermal characteristic of the battery material and also cooling and especially the cooling aspects of battery put restrictions towards the slow charging and also the fast charging. Okay. Therefore, we have to understand. And nowadays, we don't worry about the battery technology because most of the available electric vehicle models, they employ lithium-ion technology. Okay. So this is a very important thing that you have to understand. Okay. Okay. Now, we should understand we are talking about slow charging. How about sorry, we are talking about fast charging. How about slow charging? Okay. Actually, there are standards related with this slow charging and the fast charging. What do you mean by slow charging and the fast charging? What we really need, we need to get charge our electric vehicle within as fast as possible. So that is our requirement. That is our main requirement. Okay. For that, what we need is we have to feed our electric vehicle with high power. Okay. In order to achieve fast charging, we have to feed our electric vehicles at high charging rate. That is the main difference between the slow charging and the fast charging. In slow charging, we employ a small amount of power, but for fast charging, we have to give more power. Okay. Actually, in order to avoid mentioned challenges with battery characteristics, we have to use high voltages also. When we are incorporating high power, we have to go for high voltages as well. That's what we should understand. Okay. So actually, if we are going to charge our electric vehicles with slow charging, you can have 120 volt and 240 volt onboard chargers. That means charger is within the electric vehicle itself. Okay. But if you are going to charge your electric vehicles with high power, due to the weight and the construction perspectives, we cannot include the charger within the electric vehicles. We have to take that charger to the out, okay, in order to meet the power requirements. That's why we are saying off-board chargers. Okay, so you can see if you are going for level 1 charging, where the charging power is 1.4 kilowatt and battery voltage is 120 volt, to achieve 200 kilometers, we have to charge our battery for a period of 1,332 minutes. Whereas, if you are going to charge your electric vehicle to achieve the same range with ultra fast charging or the fast charging, within 4.7 minutes, we can charge our electric vehicle. It means with fast charging, we have overcome the main bottleneck, that is the long charging time. That's what we have to understand. Okay. So it is a very good advantage from the proliferation of electric vehicles point of view. Fast charging is very important because especially when we consider trips, long trips, we don't use electric vehicles due to the range anxiety. But if we can charge our electric vehicles within 4.7 minutes, of course, now we don't have any range anxiety, we can go for long trips, even with electric vehicles. Okay. But then there is another issue from where we are going to charge, because the chargers are not on board, they are off board. Of course, we can charge our electric vehicles within 4.7 minutes, but if we cannot find a charger, then there is a problem. So that's why we have to very carefully address these electric vehicle cases. However, in this slide, what I'm going to explain, according to the standards, we have several charging modes. as far as electric vehicle charging standards are concerned, we have two standards. One is IEC standards. Other one is the SAE standards. When you consider IEC standards, we have mode 1, 2, 3, and 4. 1, 2, and 3 are AC charging. 4 is DC charging. If you consider SAE standards, we have level 1, level 2, and level 3. So level 1 and level 2 are related with AC onboard charging. Level 3 is related with DC fast charging. Okay. This is what you have to understand. Okay. Actually, from the research, researchers have found average maximum charging time that electric vehicle users prefer is 15 minutes. They want to charge the electric vehicles within 15 minutes if they are in a long journey. Otherwise, they don't like, they don't want to go for electric vehicles for long trips. They need to charge the electric vehicles maximally within 15 minutes in long trips. Okay. Actually, this the 15 minutes comes from the state of charge from 20% to 80%. That means if you consider your battery, to charge your battery from 20% to 80%, the minimum required, the maximum required time would be 15 minutes in order for us to go for electric vehicles in long trips. Okay. In order to achieve this 15 minutes targets, you can see for different models, this is the minimum charging power. For this particular model, the required charging power is 69, but 69 is not available with the actual maximum, actual charging power, it is 49. So that means due to some constraint associated with this particular model, even though we need 69 charging power to achieve 15 minutes target, but we can't go for that 69. Why? With this constraint, the maximum amount that we can go is 49. So those are really challenges. Those are really challenges as far as electric vehicle charging is concerned. So that's what you have to understand. This is just sort of a game. We have to play with the users' perspectives, grid stability, and also battery constraints. It is something like that. Now we know there are two types of charging, the slow charging and also fast charging. For some electric vehicles, we can't go for fast charging due to some battery constraints and some constraints associated with the particular electric vehicle models. Okay. Therefore, what we have to understand is when we are planning fast charging stations or fast charging facilities, we have to strictly understand that in the electric vehicle field, we have both slow charging vehicles and also fast charging vehicles. Here it's very clearly you can see, these are some predictions. So percentage wise, you can see the level 1 AC charging percentage is 2% because electric vehicle users don't like to get the electric vehicle charge for long time. So that's why the percentage of level 1 is less. But still you can see the level 2 is dominating with 54% even by 2030. Okay. Here, of course, you can see somewhere around 2020, the DC fast charging is around 22%, but by 2030, it increased up to 44%. That means people are going towards the fast charging, but still slow charging level 2 is dominating. Then when you are planning fast charging facilities, (7.2 kilowatt). Then you have to understand for in electric vehicle fleet, both slow charging vehicles and the fast charging vehicles are there, in which slow charging vehicles are dominating. Then what we should note, actually the take home message of this slide is, when we are designing fast charging in the future, we can't completely forget slow charging vehicles. We should accommodate slow charging vehicles within fast charging stations as well. That's how we should design fast charging infrastructures. That's the thing. That's the take home message out of this slide. Okay. This is the charging process. This is just of an illustration of charging process. You can see here both onboard charging and off-board charging are illustrated. Okay, if you want to go for off-board charging, we have to have a specific electric vehicle supply equipment to supply your battery, okay, which is located outside the vehicle. Okay, but if you are going for onboard charging, the charger is placed within the electric vehicle. And to govern this complete process, International Electrotechnical Commission, IEC, has defined certain standards for general requirements, communications, EV connection, and plugs and cables. For all these aspects, these IEC standards have already been defined. Therefore, you have to understand that this is a very standard process, defined process. We can't plan or we can't design fast charging as often as we wish. We have to comply certain standards. Why these standards have been defined, you understood in my one of previous slide. The availability of electric vehicles on the world roads has a very big diversity in terms of the battery capacity and some other constraints. There is a huge variety. There is a huge diversity. So in order to compatible with all available models, we should have certain standards. Okay, we have to comply those standards when we are designing a fast charging facilities and infrastructure in the future. That's why these standards have been defined. Okay, that's the main idea behind this standard. Actually, electric vehicle charging is concerned, you should know IEC 61851 standard is very popular standard where all the requirements and all necessary standards have been defined. Here you can see this is IEC 62916. These standards are specifically for the couplers. That means how you are going to connect your charger to your electric vehicle. For the couplers, actually when you are design and when you are manufacturing electric vehicle supply equipments, your coupler configurations and the parameters should strictly comply with these standards. Okay, these are industry standards. CHAdeMO, this standard is widely used in Japan, and GBT, this standard is widely used in China, and CCS, that is a combined charging system, type 1, this standard widely used in North America, and type 2, it is Europe and Australia. Okay, Tesla worldwide, you know that about. The Chaoji, actually, this is a very interesting future. This is sort of a paradigm shift from my perspectives. Actually, once this Chaoji standard come into play, we can charge our electric vehicles at 900 kilowatt. Okay, so that's a very interesting thing. But they are hardly working with these standards. Actually, it is a combination of CHAdeMO and GBT standards. Okay, here you can see the maximum voltage. In order to go for these standards, the maximum required voltage is 1,500 volt. And even with these standards, you need the maximum voltage, 1,000 here with the CHAdeMO. With GBT, it is 750 volt. With CCS type 1, it is 600 volt, so on and so forth. Okay. Actually, when I was doing my PhD, actually, I have practically, and I mean, from my naked eye, I have seen 350 kilowatt charges. Okay, because in Europe, we have CCS type 2 standard. Actually, these 350 kilowatt charges are widely available because Norway is a country where government give more incentives towards electric vehicle proliferations. Therefore, they have installed electric vehicle chargers at free of charge. Okay, so but it's for a short period of time just to promote electric vehicles. Then they will go for a business model. Okay, but nowadays the people can charge electric vehicles at free of charge. Okay, so here you have to understand this charging infrastructure. When we consider the charging infrastructure and the associated parameters, they are not very straightforward, very simple parameters. Here the maximum voltage is 1,000 volt. So we should have some vision how we are going to achieve this 1,000 volt, how we are going to achieve this 750 volt. This is not very simple. We have sort of a very advanced techniques in order to go for this type of very high rated values. Therefore, now you may have a sense fast charging is not a very simple concept. It's not a very straightforward concept. We should have some sophisticated thinking or a very analytical, very comprehensive thinking towards infrastructures and other related issues or other related aspects. That's the take-home message of this slide. Actually, with the understanding of that standards or the requirements, this is the practical configuration of available fast chargers. We supply fast chargers from 3-phase low voltage network, and there are 2 conversion stage. Within the first stage, we have to convert from AC to DC, and then we have to convert that converted DC into regulated DC. For that, we have 2 conversion stage where we are using rectifier and also DC to DC converter. Okay. Actually, this is the internal architecture of the electric. Is it okay? Huh? No. Actually, in my previous slide, we understood that when we consider the electric fields on electric vehicle fleet on the world's road, it consists of both slow charging electric vehicles and also fast charging electric vehicles. Okay. Therefore, your electric vehicle supply equipment should be capable of supplying variable rate charging rather constant rate charging. In order to facilitate that, electric vehicle supply equipments are built in modular format. This is a one module, and it's okay. It's okay. Okay. In order to facilitate variable rate charging, electric vehicle supply equipments are built in a modular form. Actually, with this, we can very smoothly change the charging power. We can very smoothly change the charging power. Actually, these modules are interconnected via interconnected in parallel. Okay, therefore, we can very easily modulate your current. Okay, if you want, you can modulate discrete. If you want, you can modulate continuously. Both is possible if you have your electric vehicle supply equipment in modular form. If you consider just one module, it consists of a rectifier, which converts AC into DC, and also the converted DC will be regulated by DC to DC converter. As far as DC to DC converter is concerned, I want to highlight one fact, that is the galvanic isolation can be built easily with DC to DC converters. Actually, here you can see, if you consider the figure A, you can see the galvanic isolation is achieved with a low frequency transformer, which is sort of an expensive method of achieving this galvanic isolation. Rather, going for this type of low frequency transformer, we can have solid state transformers. Yes, we can have solid state transformers integrated with DC to DC converters. Okay, so that's a very interesting thing. You should note that. So in this slide, what we should understand, available electric vehicle supply equipments can provide variable rate charging rather constant rate charging. The important thing here, if you have variable rate charging, you can facilitate slow charging electric vehicles as well as fast charging electric vehicles, because we can change the charging power. Whenever you have slow charging vehicles, you can reduce the charging power. Whenever you have fast charging vehicles, you can increase the power. That's why the beauty of this architecture, when you consider modular architecture of electric vehicle supply equipments, actually at the moment, almost all the electric vehicle supply equipment manufacturers, they are manufacture their electric vehicle supply equipments in this form. Okay. So this is another step of this modular form. These are possible converters. VNR converter, conventional 2-level voltage source rectifier. Actually, in place of this 2-level voltage source rectifier, you can use, if you want, a 3-level and multi-level rectifiers also. Okay, this is multi-pulse rectifier. Actually, this is just to indicate how the internal arrangement, internal power electronics is built. This is not very important from from planning perspectives. Okay, this is just to understand with this architecture, with this construction, we have achieved variable rate charging as far as fast chargers are concerned. Okay. Now we understood electric vehicle supply equipment in the sense it is a power electronic based microgrid. If you have the several electric vehicle supply equipment within a fast charging station, you have another view on that fast charging station. It is not a fast charging station. It is a power electronic base microgrid. That is the idea. Whenever you have power electronic converters, we are getting these problems. We are getting voltage flickering. We are getting harmonic issues. And also here, the issue is actually not only the harmonics, we are getting super harmonics also. That means if we very carefully see the voltage and the current profile at the point of common coupling, we can see harmonic components whose frequencies are even higher than 2 kilohertz. So that we have to understand electric vehicle fast charging station issues are more severe than the issues related with solar photovoltaic system or a wind energy system. Because one aspect is the charging power or the charging demand is pulsating with the plugging and the departure of arrival and departure of electric vehicles. The load is pulsating load. It is one aspect. And other aspect is this is a power electronic based microgrid. Actually, this fast charging station is a source of harmonics to your grid. It creates harmonics and also super harmonics. So these are the real challenges that we have to mitigate when we are going towards fast charging technology. That's the thing you have to understand. Because here, I'm not going to go very much detail because this is very technical. If you consider these power electronic converters, you saw we have two power conversion stage, AC to DC stage and DC to DC stage. To control power injection, we have a voltage controller which control the DC bus of the electric vehicle supply equipment. And also a current controller. Sorry. And the current controller with which we control the current injection to the electric vehicle battery. Okay. Here you can understand that we are having constant voltage, constant current charging, or constant current, constant voltage, constant current, variable voltage charging, like that. Okay. Therefore, with this block diagram, what you should understand, power electronic fast charging station is a power electronic base microgrid where we have to have very innovative control strategies in order to control the power flow of charging, electric vehicle charging. Otherwise, we are getting very severe problem, which are more severe than the intermittency associated with photovoltaic systems and also wind energy systems. Okay. Okay. Now, this is a representation of a power, a fast charging station in a schematic diagram, in schematic view. Here, what you should understand is you should know the if you consider I mean complete fast charging station overview point of view, it exerts very high power to the power grid. Okay. Power, I mean demand requirement, very high demand requirement to the grid. Why? We understood that with fast charging, we are going to charge our electric vehicles. At the moment, I told you it is possible we can charge with 350 kilowatt. And in the future, we can go for 900 kilowatt. Let's say in your fast charging station, you have 10 charges. So it is 3,500 kilowatt. That means 3.5 megawatt total load it gives to the power grid. That's why fast charging stations are not recommended to connect to low voltage grid. We have to connect fast charging stations to medium voltage grid because of this capacity constraint. Actually, if you consider this 900 in the future, at the moment it's not available, but we know in very recent future, we will be getting fast chargers whose capacity is 900 kilowatt. Okay. It means we are exerting more stresses to the power grid with very high capacity. Therefore, we have to understand that a power grid itself, a power grid alone cannot supply fast charging station. A power grid alone cannot supply fast charging station. If a power grid is going to supply alone a fast charging station, it is a very big stress for the healthy operation of the grid. Therefore, it is always recommended to have an energy storage or a renewable energy system within the fast charging station itself. Then you should note that these are all chargers where you have two power conversion stage, rectifying stage, and also regulating stage. They are power electronic converters. The charger, hereafter we are not going to see these chargers as fast chargers. You always should see the fast charger mean it is a two-stage power electronic converters. Then you are having another challenge, that is, in order to supply the capacity in order to supply the capacity of your fast charging station, you have to have a inbuilt embedded energy storage. To regulate this power, again, you need to have another power electronic converters. Another set of power electronic converters you should have. Then altogether, this is sort of a microgrid. Fast charging station is sort of a microgrid. Here you have your main grid. This is your main grid, and this is microgrid. Okay, it's very interesting. Actually, in this schematic diagram, we have included only energy storage, but of course, you can have a photovoltaic plant, wind plant within the fast charging station as well. That type of architectures are available in Europe. Okay. Then you should note the severity. Why? In the fast charging station, we are having pulsating load. It is a one problem. And the capacity is very high. It is another problem. And if you have renewable energy systems within the fast charging station, the intermittency is also another problem. We are having three problems now we have to address. Is that clear? So, then you may think that, okay, fast charging is a set of problems. No, we have smart solutions for this one. Okay. Why we are understanding problems or the issues, then only we can provide sustainable solutions. So that is why today I'm focusing the prospects and also the challenges of fast charge. That's the thing. So here there is another architecture. That means this is known as the centralized architecture for a fast charging station. The figure 11 illustrates the decentralized architecture for fast charging station, where you can have separate energy storage for each and every electric vehicle chargers, but it is not very practical. The practical version is centralized architecture, where you have a one energy storage within the fast charging station. Okay. Since I'm going to discuss this all aspects in my next part of the presentation, I'm just skipping this slide because then you will not be getting very clear understanding about the content. If I'm going to explain everything here, I will explain the all information available in this slide in my subsequent slides systematically. Okay, so therefore, for the moment, I just skip this. Actually, before going to my next part of the presentation, now I would like to summarize what we have studied so far. Of course, as far as electric vehicles are concerned, we can consider it is sort of clean or sustainable mode of transportation. Actually, this sustainability and this greenness, the cleanliness comes with the less contaminant associated with the emissions. And also, with the perceptible advancement of battery technologies associated with especially lithium ion, now we can go for very high power densities and also very high energy densities when we manufacture electric vehicles. It is a very good aspect. It's a prospect. Okay. But when we are going towards electric vehicles, we understood that there are 3 modes, there are 3 levels: level 1 charging, level 2 charging, level 3 charging. With level 1 charging, we understood that in one of my previous slides, in order to achieve 200 kilometers, we need to charge our electric vehicles for a period of 1,332 minutes. Whereas if I employ fast charging, level 3 charging, where the charging rate is 400 kilowatt, I can achieve the same kilometers within 4.7 minutes. Then with the slow charging, our problem is long charging time. Okay, that's why people prevents from purchasing an electric vehicle, because they don't like to wait for long time to charge the electric vehicles. What they need is, they need sort of a similar experience in terms of refueling their electric vehicles, just like gasoline counterparts. Because when we consider the gasoline vehicles, we can refuel our vehicle with a very short period of time. So we need that same experience even with electric vehicles. So that's why people don't like for electric vehicles, especially in long trips, because in long trips, we can't wait very long time. So that's what you can understand. Another thing is the range annexity. With one charge, how far we can drive our electric vehicle. It is a serious concern. We understood that one, okay? In order to avoid this range annexity, in one of my slides, you understood that we have to go for high capacity electric vehicles. But when we are going for high capacity electric vehicles, we have to pay a lot of money. So it is another burden. It is another burden. Then long charging time is one challenge, and the range annexity is another challenge. I told you, according to United Nations reports, by 2050, our population is going to be 9.5 billion. We can't expect that all these people do have detached houses. Therefore, if we are going for level 1 or level 2 onboard charging, we need to have a separate, dedicated house in order to achieve overnight charging. So we have, once after our work, we have to go home and plug our electric vehicle to the charger. Throughout the night, electric vehicle get charged. But due to some space constraints, we can't expect each and every person in the future will be getting a detached house. Because of that, people are reluctant to buy electric vehicles. It is another challenge. So those are the things that we have discussed in the first part of my presentation. And I'm sorry, what happens? Okay. Okay. Now, then we realize that in order to avoid all these challenges, currently DC fast charging is emerging. When you have fast charging, you are giving a very good solution for long charging time. And then we have to, of course, think about the range annexity, because I told you, according to the nature of the electric vehicle supply equipment, we cannot install electric vehicle supply equipment inside the electric vehicle. When we are going for fast charging, we have to take it out as off-board charger. Then, in order to avoid range annexity, we have to have a widespread of charging stations all over the country or a certain region to avoid this range annexity. Otherwise, what happened? We are going with a low capacity vehicle. Whenever the charging demand comes up, we have to find a charger. If the charge is not available, still this range and anxiety problem is there. Therefore, in order to avoid the range and anxiety, we should have a widespread charging network for fast charging. So that is also there. Okay. That's why the first challenge is the DC fast charging. Or of course, with the DC fast charging, we can give good solutions for the mentioned challenges. But then we are getting another problem: deployment of charging stations in a widespread manner. That is also a challenge. And then we understood that when we are going for DC fast charging, it exerts a big stress to the power grid with added, extra load, because EV charging is another extra load to the network. With that extra load, what happens? EVs add an extra load to the network. Because of that, we have to have some issues with the network capacity and power system stability and power quality issues. We understood that DC fast charging station is nothing but a power electronic based microgrid. Whenever you have power electronic based microgrid, we are getting issues like voltage fluctuations. As far as voltage fluctuations are concerned, we are getting rapid voltage changes and also the flickering and voltage drops or voltage rise. But when you are having fast charging stations, of course, we are having voltage drops. Okay. And another thing, then it is related with the power system stability problem and the power quality issues. So those are very well-known problems when we consider fast charging stations. And there is another problem, due to this added load, due to this extra load, we may have to reinforce the existing grid. We can't run the existing grid with the same structures or the as it is. We have to reinforce it. We have to, or else we have to reconstruct some portions of your grid where you have very high grid impedance. Or in other words, you have a very weak grids. Okay, so that is another issue. And in Sri Lanka, of course, this is not a very serious problem. Electricity market, as we don't have a very serious market with the energy, but immediately we have to go for this one because when we consider European market, it is a very interesting trade. I need to tell you some important thing related with this market operation. Ultimately, the subscribers or the customers are the people who are getting benefits over this market. Therefore, the monopoly structure for power distribution or the power generation is not suitable. We have to detach or descend. The good term may be restructuring. Okay, we have to go for restructuring as far as electricity market operation is concerned, with which subscribers are getting more benefits. So you have to understand now, these are the negative impact associated with electric vehicle fast charging. Now let's see what are the probable solutions that we can propose to mitigate these mentioned problems or the challenges. Actually, I told you fast charging can provide very good solutions for long charging time, range anxiety, autonomy related issues. But we have to focus on deployment and charging management of the operation of fast charging station. Why? Because this is a power electronic based microgrid and it has a pulsating load It is not just a constant load, it is a pulsating load. Then if you consider this pulsating nature of this load, it is something severe than the intermittency associated with renewable energy. Therefore, we have to very carefully address the energy demand or the charging which is taking place, which is going to be taken place within a fast charging station. Then you should note that a fast charging station is a very good business model. We can't afford fast charging station, or actually we can't allow electric vehicle users to charge their electric vehicles at free of charge, just like in Norway. In Norway, of course, we can find certain places where public chargers are there, where electric vehicle users can charge the electric vehicles at cost, free of charge. But we can't afford that as a country. Definitely, we have to go for a business model. With a business model, we have to address all the mentioned challenges that I have mentioned before and I have summarized before. So that is the way we can utilize electric vehicles in our roads. This should be given to private sector to install charging stations. And there should be a regulating body to regulate grid stability aspects, and maybe some user convenience aspects. Therefore, we should understand that in order to promote electric vehicles, fast charging is a very interesting alternative, very suitable alternative. But when we are deploying fast charging stations and coordinating the charging process within the fast charging station, it should not be an ad hoc decision. We have to pay some strict attention in order to deploy and manage the charging within a fast charging station. That is the conclusion. So now what we are going to just overlook, what are the available techniques with which we can properly deploy a fast charging station, and also how to coordinate charging process that can take place within a fast charging station. Actually, with this, I want to highlight another fact. If you want to integrate more renewable energy, of course, we should have a stable power. There is no doubt about that. But at the same time, if you consider countries like Germany, Denmark, and Norway, they have very comprehensive analytical model, computational model associated with their renewable energy systems. That is the main key of their success in integrating large amount of renewable energies into the power grid. If you just consider Denmark, their peak demand is somewhere around 7,000 megawatt. If it applies for Sri Lanka, I think it is around 2,700 megawatts, okay, at the moment. But in Denmark, it is around 7,000 megawatt. But in order to achieve this 7,000 megawatt, they have installed capacity altogether 18,000 megawatt. Out of 18,000 megawatt, 6,000 coal power plants, 6,000 wind energy, 6,000 interconnections. Because in Europe, they have interconnections among other countries. So altogether, they have 6,000 megawatt interconnections with which they can export or import energy. Actually, without this, they can very nicely handle, they can very nicely control their power grid without having any problem. The main success behind this is they have very strict grid codes, very sophisticated and very comprehensive grid codes. Another thing is all these grid codes are based on a comprehensive analytical model, comprehensive computational model. Therefore, our prime motivation towards charging management of an electric vehicle fast charging is also we should know the information related with the physical model, physical layer. On top of the physical layer, we should have very comprehensive computational layer. Now, I'm going to explain what sort of computational layer we should have in order to overcome the problems that I have mentioned so far. This is just an overview. This is just a very simple overview because it is, I can't actually explain the complete computational model within 1 hour or 1.5 hours. It's that much complex, but I'm just explaining in a very simple way about this computational layer. Before going to the computational layer, what we have to understand is we are having severe problems related with the physical layer. We understood about that. All these issues can be very nicely handled if you have a comprehensive computational layer on top of this physical layer. That's the conclusion. In order to develop those computational layer, these are the main objectives because we are doing a business. Therefore, we have to maximize the profit of the fast charging station. That is the main objective. We have to maximize that one, maximize the profit. And the second one is the minimize the impact to the power grid and also the energy market. We understood there are certain impacts towards the energy market and also the power grid. Then when we are developing these computational models, we have to minimize all these issues related with stability and also the market operation. And I told you this is a business. In order to have sustainable operation of this business, we have to retain our customers. Our customers are electric vehicle users. Therefore, we have to provide a quality service to electric vehicle users. Those are the main 3 objectives that we have to consider when we are developing a computational layer to control or coordinate the charging of an electric vehicle fast charging station. Okay. Actually, these 3 objectives are achieved with this main 4 subtopics. Deploying a fast charging station is not an ad hoc decision based on the availability of land near to a urban area or near to a highway road is not a reason to establish a fast charging station. We have to find the optimum sitting and the optimum sizing of the fast charging station. Otherwise, we are giving severe problems to the power grid and also to the society. Another thing is, once you obtain the best place with the optimum number of chargers, then you have to size your charging stations optimally. That is the next step. And once you establish your fast charging station, then you have to define strategies with which manage your charging demand and also schedule your electric vehicles. Finally, you should have some models with which you can analyze the overall performance of this process. This is how a comprehensive computational layer is designed. Okay? Actually, in order to design this comprehensive computational layer, we can incorporate many techniques, AI and some other computational techniques you can use. Okay? Actually, this is the main task of engineers in European countries. They are doing these things. They are developing these models, and they are communicating with academics. Okay, I have involved several projects where we have developed algorithms and also coordination theories for photovoltaic systems, wind systems, like that. Actually, in Europe, basically, they are looking very much ahead. To be honest, my PhD coming to play in 2040. For 2040, they are expecting sort of problems associated with the fast charging, and they are finding solutions now in order to cope with those problems that may come into play in 2040. Okay, so that's why I told you we should have a very comprehensive computational layer on top of renewable energy systems and fast charging station. Why? With that, we can cope all these challenges very nicely. Okay, so that's how basically European market is defined. They just predict the tomorrow demand, and also they just predict the tomorrow, or it means a day ahead power generation associated with wind, let's say. Then they are finding opportunities whether we can export some excess energy to maintain the frequency. To maintain the frequency, they are just checking whether we can export if we have some excess. Because in European system, what they think, curtailing power is not a suitable option. It has a severe cost. So we should not go for curtailing. We should do business. If you have excess energy, we should do business. That's how they think on renewable energy systems. So then they have sophisticated and very comprehensive analytical systems with which they just consider the day-ahead demand and the day-ahead generation. First, they check whether we can export at a very high cost. If it is not possible, then they are just reducing the price so that electric vehicle fast charging stations type, the flexible loads can accommodate or not. You understand? In order to accommodate this type of market operation, they have basically basic three markets: day-ahead market, intraday market, and the balancing market. With that, what they are doing is they are very nicely utilize their excess energy into a business. They are in some cases the distribution companies, okay, they are doing a very interesting business, okay, by providing these analytical services to customers. Actually, in my place, I mean my board, my accommodation, since I'm aware about this coordination things, I have done all these things by myself. That facilities are there. If you want, you can manage your load by yourself, because today at 6 o'clock, we know what happens in tomorrow. Then we can schedule all our cooking and our heater, water heater, and all these things we can very nicely schedule. And interesting thing is, I was participating for some of ancillary services, managing ancillary services also with my water heater. So I should schedule my water heater so that it manage the frequency variation of the grid. We can do that one. All the facilities are there, smart plugs are there. We can very nicely control all these things. Why we can do that? We have a very comprehensive analytical model. There are certain companies, what they are doing is, they are doing all these analysis. So that is the main duty of these companies. You understand? That actually sometimes I have purchased negative energy at negative prices. With that, what I'm doing, I have achieved my energy requirement and also I earn money. So if you're very intelligent, okay, then you can schedule your all loads in that way. How this has happened, whenever you have excess power, these generation companies, they are first attempting to export that energy. If it is not possible, they just reduce the price of this energy so that flexible load can utilize this excess energy. Even if there is no any flexible load to utilize this excess energy, they put it negative. You understand? They put it negative. Then what happens? These distribution companies, what they are doing is they are very nicely schedule their energy storage and some electric vehicle chargers, all these things, so that purchasing the energy at negative price. You understand? That type of a very complex, very comprehensive market is operating in overseas countries. To do that, we should have a computational layer. So we understood all the problems, all the issues associated with the physical layer. Now what we are trying to do is we are trying to find the solutions for those problems with a computational layer. So that's why very near future, we have to have some comprehensive computational models for our renewable energy systems, for wind systems, solar photovoltaic system, even for mini hydros. We should have very comprehensive models, analytical models. To develop these analytical models, you can utilize these concepts. Okay. So that's what I'm going to look at in my second part of the presentation. Actually, this is the last part of my presentation. Okay. Of course, if there are two parts, the second part is going to be the last part. Okay. So firstly, we have to focus how to deploy a fast charging station. I told you it is not an ad hoc decision. We have to perform comprehensive analysis in order to place or establish a fast charging station. For that, we have to perform deployment analysis. It basically consists of two parts: finding the optimum place where we can establish the fast charging station. Another one is the optimum size, optimum number of chargers we can construct within that site. Okay. Actually, this is what we are going to do under this optimum sit-in and sizing. Let's say in this particular area, I just want to build a fast charging station. Then what I'm going to do, I consider several zones within that area. And first, I have to model the probable traffics in these areas. For that, we can take several techniques in order to obtain the optimum location. We are focusing some perspectives or some objectives to find the sitting and sizing problem. And we will see what are the typical techniques with which we can perform these things. one is the construction cost aspect. Another one is the service quality aspect. I told you, if you build a fast charging station at a certain location, you should focus very strictly towards the service quality of customers. Otherwise, outsiders or the customers may not reach your fast charging station when it is in operation. Therefore, you have to pay the service quality aspect. In the service quality aspect, in practical models, I have seen charging time, waiting time, blocking probability, and sometimes the preempting probability, and those parameters have been considered to develop deployment problems. Mostly, waiting time is the parameter the developers have used in order to consider service quality. Because let's say you are reaching a fast charging station, and if you want to wait for a long time before plugging your electric vehicles to the charger, then the next time you may not reach that charging station. That's why at the first step, we have to model the traffic. We have to model the traffic within that area, okay? So for that, we can use graph theory and those mathematical techniques we can use. You understand? It may be AI, okay? Maybe AI you can use, okay? And with those models, in order to construct this deployment problem, you can have service quality aspects as one of your objective, okay? Another, this is a very important, grid stability aspect. So in each and every area, you have to consider the grid stability. What is the grid impedance here? What is the grid impedance here? What is the grid impedance? So on and so forth. You have to consider the healthiness of your grid in corresponding zone where you are going to build your fast charging station. Otherwise, you are making severe problems to the healthy operation of your fast charging station, okay? Then we have certain objectives. We need to minimize the cost, construction cost. We have to enhance the service quality of electric vehicle users who are reaching your fast charging station, and also the grid stability aspects. When you are considering grid stability aspects, you can consider transformer overloading and also the load variances. Load here, for an example, I will develop an optimization model where my main objective is to minimize the load variances. If I do my model in that way, then I'm not exerting serious pulsating loads to the network. So that's how I charge my electric vehicles. You understand? What we understood, if we are going to plug your electric vehicles in uncoordinated manner, it results a pulsating load. It results a pulsating load. But now, how I'm going to plug my electric vehicles, not in a random way, not in uncoordinated way, there is a certain coordinated manner, or there is an algorithm with which I'm going to allow my electric vehicles to plug into my fast charging stations so that suppressing or damping out these load variances. I can design my charging process in that way. So that's why I told you we should have some comprehensive computational models with which only we should operate the fast charging stations. Otherwise, we are creating severe problems to the network. That's the thing. So it's very clear now. We are having certain objectives. And let's say I want to minimize my load variance. When I'm going to minimize my load variance, some electric vehicles may have to wait because I'm going to change the plugging time of the fast charging station. If I'm going to vary my plugging time, it may affect to the service quality of the electric vehicle users, because I don't allow electric vehicle users to connect their electric vehicles as soon as they arrive to the fast charging stations. They have to certain time. They have to wait certain time. So, but I don't want to compromise the service quality of my users. Therefore, I just give constraint to my model. The waiting time should not be exceeded this amount, something like that. So you have sort of constraints and you have objectives. Interesting thing is the optimization model. Okay, so these are some practical models. But what you have to understand is, if you are building a fast charging, for that particular fast charging, you should have a specific optimization model. So you can't just take one optimization model, maybe in some other country, and you can't to take here and plug it. No, it's not very effective. What you have to do is you have to have a specific model for that one. Because I have personal experience in Norway. We develop sort of algorithms for a project like Scarpness. It was a Norwegian Research Council funded project, but there were some other institutions like Agd Energy and some other institutions. They are also supporting this project. Actually, it is a solar village. It was a solar village. We had severe issues related with the power quality and also voltage rise issue. So we developed decentralized algorithm to manage the power flow, manage the power flow within the distribution feeders. In order to do that, we can't use available models. We have to consider the situation, and we have to consider some practical aspects within that particular Scarpness village. And based on that, we have to develop the Scarpness village specific programs to manage the power flow. So that is the main success behind European power management. For each and every plant, they are having their own computational models. Okay, before establishing a fast charging station, they are communicating to the academics, and we are having collaborative projects. So we all together, we are developing very interesting algorithms with which we can very nicely handle many problems which are in the physical layer. So that is the key success behind increasing more penetration of renewables and also increasing more penetration of fast charging stations into the grid. What we should, all the time I'm saying, we should have a physical layer, but for all the problems, we can't find the solutions, the appropriate solutions within the physical layer. There should be a very comprehensive analytical layer or a computational layer on top of the physical layer. Then we are having a very smooth operation within the system. So that's the main success behind very high penetration of wind energy in Denmark. So I told you the installed capacity is 6,000 megawatt. One day, when I was doing my research, I just see how the power variations, the power flow variations in all over the Denmark. What I understood, actually, I accessed the total information somewhere around 10 o'clock or 9 o'clock. At that time, the peak demand was around 6,500 megawatt. Out of 6,500 megawatt, 4,000 megawatt was from wind. So only very few amount at that time, the Denmark grid took from the coal power. So how they have achieved this? They have very, very comprehensive grid codes. They are very comprehensive grid codes. So they are not very simple grid codes. So how we can go for that type of grid codes? We should have a very comprehensive computational layer. Then we can define very, very sophisticated, very specific grid codes to control all the problems. They are very accurately control their frequency without having any problem, even with this wind energy. And for my interest, since I knew the previous day, the wind share is 4,000 megawatt, I just see the following day, the wind share somewhere around 10 o'clock. Then I realized that suddenly it was down to 18 megawatt. So you see the variation from 4,000 megawatt to 18 megawatt variation was there. So it is very interesting. Actually, you may the most of the people are saying that in practical setting, integrating renewables are not good. We are giving many issues to the healthiness of the power system. Yes, that is true. If you don't have a comprehensive computational layer, and of course, there should be a backup. That means a stable backbone you should have. But unfortunately, in Sri Lanka, our backbone is very expensive because it is thermal, diesel, and some naphtha based stable power we have, but we don't have much coal. I don't know why. We have not gone for coal power in, long time before, where coal used to be a cheap source of energy, or something like that. It is another discussion, interesting discussion. Just go away. Sorry for that one. So another thing is the graph theory based model. Actually, if you are going for a graph theory based model, this is just to model your traffic. With the traffic model, you should have an optimization model in parallel in order to find the optimum location for your fast charging station. Okay. And queen theory based model. This is also very interesting mathematical technique with which we can forecast the future. Okay. Actually, we are using Markov chain based models, Markov decision process based models, and reinforced learning. All these things you can accommodate as a typical techniques under queen theory. Okay. But please believe me, in agro energy and that type of institutions, the engineers, what they are doing is developing these models and updating their grid codes and all these things. So we have to go there. So that is the future. Without this, we don't have any future. The renewable is the future. So for that, the main thing, we should have a backbone, very strong, stable power. Okay. Another thing is comprehensive computational layer. So that's a very interesting thing. With that, what we can do is we can increase the synthetic inertia of the grid. That is the interesting thing. We can increase the synthetic inertia. Okay. So we are talking about the mechanical inertia all the time. Okay. We can't avoid very large power plants. We can't avoid very large power plants because we are sacrificing the inertia of your system. But please believe me, maybe 20 years before, then Denmark used to be 10 gigawatts installed capacity of coal power plants. Now they have reduced 4 gigawatts coal power plants. At the moment, they have only 6 gigawatts. That means 6,000 means 6 gigawatt. But what their plan is, their plan is to reduce another 2 gigawatts by 2040. That means by 2040, they are having only 4 gigawatts coal power. And how they are going to compensate that 2 gigawatt? They are going to increase more wind energy. How they are going to do that? They are increasing the synthetic inertia with sophisticated controllers. Okay. Actually, for a photovoltaic-based system in Norway, for a photovoltaic-based system, we design, myself and my professor. So we design a one controller that is based on finite state machine. Okay, finite state machine, we design a controller. So with that, we maintain the frequency of the photovoltaic based power grid within 49.98 to 50.02. Okay. Very strictly we can do that one. For this year, I will be getting a presidential award for that work. Okay, because I included University of Ruhuna affiliation, because we have to give credits for our Sri Lankan institutions also. Since I was attached to, since I'm attached to University of Ruhuna, I included that affiliation also. Therefore, for that I got presidential award. So that means it is not, in what I want to highlight, it is not impossible. In achieving 80% renewable is not impossible at all. Because I have many experience and many examples. I can give many examples in European system. The main, actually their main success is a very comprehensive energy market and a comprehensive computational layer. And their physical layer is also a strong one as compared to our system. It is also a strong one. So with that, definitely we can go to renewable energy. So our transportation should be renewable energy based transportation. Without that, we don't have any future. Okay, so this is the key, and this is the success. These are available practical models I'm explaining today. Okay. So once you perform all these analysis, we have ended up, this is the best place where we can locate our fast charging station. Actually, we are ended up with the location, not only the location, with the optimum number of chargers, whether it is 10, whether it is 15, whether it is 12 or something like that. Why? We cannot compromise the service quality of the users. So that is the thing. And now you know the number of chargers. Let's say maybe 10, maybe 12, maybe 15. You know the number of chargers. Then you know another fact. This is a power electronic based microgrid. Therefore, we are having pulsating load, and we are giving extra load to the grid. Therefore, we should have a we should have a renewable energy system or energy storage, local energy storage or a local renewable energy system within the fast charging station itself. Therefore, how we are going to construct this photovoltaic plant and the energy storage, it is also not going to be a ad hoc decision. Okay, we have to perform techno-economic analysis before installing the photovoltaic plant and the energy storage. So we optimally design the required energy storage. We optimally design the required photovoltaic plant. So for that, we have performed analysis. All these analyses are known as techno-economic analysis. This is also nothing but optimization models. Okay. Now, so you now you are in a certain point, no certain position in my presentation. Now we have deployed our fast charging station with optimum number of charges. Now what we are going to do? Now we are going to manage the charging process within the fast charging station. Now we are in an operating stage. Electric vehicles are reaching to the fast charging station. They are plugging into the chargers. The charging process is taking place at this moment. So we can't let it to be uncoordinated. If you left uncoordinated, you are creating many problems to the grid. Therefore, we have to coordinate the charging process that is taking place within the fast charging station. So for that, we have to propose charging coordination models. Basically, when you come to charging coordination model, it consists of charging management, or in other words, optimum scheduling, and the overall performance assessment models. So we have to have some understanding understanding between these two terms. So here you can see, okay, before going to this figure, I just recall what we have studied in the first part in my presentation. I highlighted one fact. We understood our electric vehicle fleet consists of not only slow charging vehicles, so not only fast charging vehicles, but also slow charging vehicles. In the percentage we saw, maybe in China, slow charging vehicles 44%, sorry, fast charging vehicle going to be 44% by 2030, whereas fast charging, slow charging, level 2 slow charging going to be 54%. Can you remember? It means when we consider the fleet, still slow charging vehicles are dominating. And also I told you, when we construct electric vehicle supply equipment, they are constructed in modular way, with which we can provide variable rate charge, not just constant rate charge. Whenever you have slow charging vehicles, you can accommodate slow charging vehicles. Whenever you have fast charging vehicle, you can accommodate fast charging vehicles. Therefore, if you just consider this particular charger, you can charge slow charging vehicles and also fast charging vehicles. Whenever you are having slow charging vehicles, it takes certain time. Therefore, you can optimally schedule those charging processes. EV1, EV2, EV3, they are slow charging processes, which take significant amount of time. How we are going to perform this type of slow charging with a schedule? We don't let slow charging vehicles to connect as often as they wish, or else upon their arrival. We are not going to do that one. If we are going to do that, we are tarnishing the stability of the power grid. So what we have to do, we have to plug them into the fast charging station in a sort of a schedule. Okay, so that's what we have to do. But with the slow charging vehicles, but with fast charging vehicles, it is not possible because it's a very small time significant with respect to slow charging vehicles. Therefore, for fast charging vehicles, we don't care about the total charging time. Whenever they come, they can just connect the electric vehicles to the charge. Okay, but yes, that is the basic understanding. But however, we allow electric vehicles, or if and only if these all the constraints are met. Otherwise, we are not going to connect fast charging vehicles. So that's the key behind this one. So that's how we are performing this charging management and optimum scheduling within fast charging station. And the overall performance is actually we just overlook the operation of the fast charging station. We know the total number of traffic flows, and we know the total number of traffic inflows and outflows. Let's say if you are having very high blocking probability, then it is not a good charging mechanism. Why? If your blocking probability is high from the overall perspectives, then it is not sustainable way of operating your fast charging station. After some time, you will lose your potential customers due to high blockage. Let's say if your overall or average waiting time of your customers is very high, then it is also a not good method of controlling or performing the operation of your fast charging station. ultimately what happens, you will lose potential customers with the passage of time. Therefore, what you should note, we have charging mechanisms with which we are optimally utilize the charging resources, maximize our charging profit, while giving quality service to customers also. We are doing this type of thing. Actually, the available models, they are, we say, hierarchical models. Let's say the lowmost layer you can consider as charging station, let's say, and they are communicating to upper layers, so on and so forth. We can develop our overall charging management system in hierarchical architecture. Okay, something like that. So here also the same. In order to develop this charging management and the optimum scheduling models, these control aspects, timing aspects are considered. If we go for control aspects, basically with the available models, we can see economic aspects are considered and operation aspects are considered. Actually, when you come to operation aspects, you can see optimum utilization of charging resources and some user preferences, plugging and plug out time, waiting time, day-to-day frequency of plugging your electric vehicles, charging time, etc. have been considered. The service quality we studied in a previous discussion, what is the service quality, and also grid stability measures are considered when charging management algorithms are developed. Okay, therefore you have to understand it is not uncoordinated process. It is a coordinated process by considering these aspects. Okay. And the other thing is the timing aspects, because we should not, offline strategies are there. That means we have, in some case, we have to schedule or we have to plan how your fast charging station operation going to be 24 hours ahead. So that type of strategies are known as offline strategies. And how your charging process is going to take place real time is going to be the online strategy. Okay, but with the online strategy, we are getting serious challenges related with the demand uncertainty and the energy price uncertainty, power supply uncertainty. Because of these uncertainties, we are getting serious problems when we are developing strategies. Okay, so these are the typical techniques. Optimization models, of course, we can use. Linear, quadratic programming, stochastic programming. I don't want to go much into these things, but when you are developing your models, your analytical models, or the your so then you can develop these computational models. Okay, and heuristic algorithms, maybe just like genetic algorithm, or you can have your own heuristic algorithm, of course. And Q-based models, as I told you, Markov chain, Markov decision process based algorithms you can develop. Okay, in order to develop those algorithms, you can consider energy price, or power or energy. It may be real time or forecast, or EV mobility. I told you in some aspects, the actual data might not be available. Then what happens? We have to go for AI-based models or Monte Carlo simulation based models, so on and so forth. We have to go for some modeling techniques in order to work with this EV mobility. And the utility constraints, of course, you are getting utility constraints, you are getting grid constraints. In my first part, I explained what sort of battery constraints we have to consider when we are going for fast charging, okay? And the user preferences. All these things we can encounter in order to develop these charging coordination algorithms. Actually, that's why I had a first part, because without the first part, this is not really possible to explain. Since with the first part, you understood all these things, the battery constraints and what are the user preference and all these things. Now, you can very easily understand how we should develop these charging coordination models. Okay, these are all computation layer work. So this is sort of one example. Here you can see this is the operation of the fast charging station. For the fast charging station, for this fast charging station, there is a dedicated energy controller, okay, that governs the energy flow into this fast charging station. Actually, this energy controller communicates with the upper layers. This upper layer may be a company which owns several fast charging stations when we are developing business models. Okay, so then this particular company communicate with the electricity spot market. I told you we should have, when we are having renewable energy penetration, it should happen according to a market. Then these entities, especially these fast charging stations, they are going to work as flexible loads. Then they are communicating with the spot market or the energy market. Then they purchase these energy controllers, or these charging station controllers are purchasing the required amount of energy from the market, okay? And they are making their operation. Okay. Since we have a very strong physical layer, and this is sort of a computational layer, with both, we can avoid all the mentioned issues very nicely. Okay, so that's the key success going this type of systems. And I don't want to explain overall assessment. I explain you in the overall assessment. Basically, what we are doing, we are considering the traffic inflows and the traffic outflows, what is happening within the fast charging station. All these things we are analyzing. In that particular case, I told you we should have some EV mobility models. Maybe these models are AI-based models or Monte Carlo simulation-based models, something like that. We have to model this with the knowledge of available electric vehicles within that particular region, not only the available traffic, but also we have to consider the probable traffics within that particular area. Because when we are going for, if we are going for the fast electric vehicle fast charging, okay? So our I mean electric vehicles as our mode of transportation, then we should have a widespread network of fast charging station. Okay, then what we should note, we have available traffics and also probable traffics within that particular area. We have to consider both. Okay, that's why we have to have some interesting models to model EV mobility and this admission, how the things are happening within the fast charging station. All these things we have to analyze. The techniques are available. examples are available. Only the thing is, we have to take it and get it, and there should be some crew. They have to analyze what are the requirements and what are the inputs. With that, we have to develop dedicated models for that particular fast charging stations. Okay, so that is the key success of the operation of the fast charging station. Basically, I covered how the fast charging station should deploy, how we should optimally size your fast charging station, and how you manage the operation within the fast charging station, and how to analyze the overall performance of your fast charging station as conclusion. Okay, so those are the typical analysis that we have to perform pertaining to the fast charging station operation. Okay. So in today's talk, we started with sort of a motivation that to cater this 2 billion probable traffics or the probable vehicles in 2050, we have to go for sustainable mode of transportation with electric vehicles. Some governments, they are having accelerated programs with which their citizens are motivated towards purchasing electric vehicles. And in that case, we understood certain issues related with electric vehicle itself and also the charging perspectives. And I explained how the electric vehicle chargers are built. We have basically level 1 charging, level 2 charging, and level 3 charging. With level 1 and level 2, we have to sacrifice a lot of our time. That means it takes a lot of time to charge our electric vehicles. It put a lot of barriers for electric vehicle users to buy, or the vehicle users to buy an electric vehicle. As a solution, we can introduce fast charging. With that, we can charge our electric vehicle as fast as possible. But when we are going for fast charging, we are creating a lot of problems to the stability of the electric grid, and also the user preferences and the user satisfaction perspectives. In order to address all these issues effectively, of course, we should have physical layer mitigation issues as well as computational layer mitigation issues to avoid these issues and to go towards the electric vehicle fast charging state, electric vehicle proliferations in a very high numbers to go for sustainable mode of transportation. So that is the end of my talk. Okay, so I believe we should go for renewable energy based sustainable transportation in very near future. Thank you.
Good evening, all. Thank you very much, Dr. KMSY Konara, for your valuable time with us and for this wonderful session. And now we have come to the end of today's session. And for online news, if you have any questions, you can raise your questions through the Zoom chat. Otherwise, we can continue with our next item. So we have arranged a token of appreciation for our guest speaker, and I cordially invite Engineer Dushant Vanyarajji, Chairman, Electrical, Electronic and Telecommunication Engineering Sectional Committee, and Engineer Verang Dasanayaka, the Deputy Chairman, Electrical, Electronic and Telecommunication Sectional Committee to the podium, and I cordially invite our guest speaker, Dr. KMSY Konara, to the stage. Thank you. So now I cordially invite Engineer Veranga Dasanayaka for delivering the vote of thanks. Over to you, Engineer Veranga.
Thank you. Good evening, ladies and gentlemen. On behalf of Electrical, Electronic and Telecommunication Indian Sectional Committee, I extend really hearty vote of thanks for our guest lecturer, Engineer Dr. Konara, who is a senior lecturer of Department of Electrical and Information Engineering, University of Ruhuna, who accepted a short time invitation and spent time from his busy schedule to grace this occasion. Today we had a great opportunity to get valuable knowledge on prospects and challenges of electric vehicle fast charging, which is widely discussed in forums these days. Engineer Konara is an expert in renewable energy sector who has done many researches internationally on renewable energy systems, charging coordination of electric vehicles and smart grids. Today we are know all engineers and professionals migrating from Sri Lanka. So I especially would like to thank Dr. Konara for coming back to our country and uplift our motherland, and really appreciate your contribution and dedication to teach our young engineers and improve their knowledge on to international level. Next, I would like to thank the previous committee chairman and the deputy chairman and all other committee members for helping us to organize this event successfully. Also, I would like to thankful to the engineers of Sri Lanka Administrative Division, Publicity Division, and all other staff members of IESL for their valuable support given to make this event a success. Finally, my gratitude goes to all committee members, all members of IESL, and other participants who joined with us in person and via online platform for spending your valuable time with us. As Electrical, Electronic and Telecommunication Section Engineering Committee, we are willing to organize this kind of public lectures, seminars, webinars, workshops, field visits during this session 2023-2024. We expect your contribution and fuller support like this in future events also. Thank you very much again, all of you and those who forget to mention their names personally. I wish you all a very good evening. Goodbye.